finished up last time. We worked through partitioning variants, got everything squared away in terms of our hand calculations here. Turn off there we go. Okay. In terms of getting our ANOVA table populated here and making sure everything's teased apart with stuff. Okay. And so remember what we had looked at here. We had our example was a 2x2 design where we're looking at the impact of arousal and task difficulty on performance, right? And so with this 2x2 design, what we're going to end up with is we're going to have a significant main effect of task A, right? Christine, can you tell me how do we interpret? Say I have a significant effect of a significant main effect of task difficulty. What does that mean?
So I think it was it like low, medium, high task difficulty?
And it was just, I think it was, yeah, it was actually low. So it's a 2x3. Okay.
2x3.
Yeah.
So that means that depending on the task difficulty, that changes what we're measuring. I forgot what we're measuring too.
Is your performance?
Performance, yes. So
okay.
Performance depends on the task difficulty.
Okay, perfect, right? So again, this starts to get tricky when we're thinking about these factorial designs. This main effect of task A, if we've got 3 levels of, okay, we've got 3, okay, so this was a 3x3, not a 2x2. So we got a 3x3, so we got 3 levels to factor A, 3 levels to factor B, and then an interaction, right? So my significant effect of task difficulty says collapsing across arousal level. All right, nope. We've got a 2x3. Easy, difficult, 3 levels of arousal. Okay. So if I've got a main effect of task difficulty, that's saying I'm seeing differences in performance in easy versus difficult tasks, irrespective of arousal level. Right. So collapsing across arousal, just on average, if I look at the average of easy performance in easy tasks and the average of performance of hard tasks, we're seeing some sort of difference there. Okay. And silently eyeballing this graph, what does this graph tell you, or what would you suspect is the main effect of task difficulty here?
Well, if it is, they have low arousal when I was looking at that one. I was like, I just struggled. When they have low arousal.
We're ignoring arousal. We're just looking at the main effect of task difficulty. What's the main effect of task difficulty based on this graph?
As their performance gets higher with these, sorry, not.
Someone help her out? What are you thinking?
Just the easier the task, the greater the performance?
Yeah, perfect, right? Main effect of task performance here is that on average, people perform better at easy tasks versus hard tasks. What are you seeing here with that thing?
Just comparing the blue and the red, the
yep.
blue bars and red.
Exactly, right? On average, if we're looking at sort of the level of performance in the blue bars versus the red bars, this is just saying collapsing across arousal, people tend to do better with, or tend to perform better on easy versus difficult tasks. So that's our main effect of task. We also have a main effect of arousal level here tomorrow. What is this main effect of arousal indicate?
That low or high arousal are resulting in similar performance compared to medium.
Okay. Close. How many levels of arousal do we have? 3, right? So if I have a main effect of arousal, what does that suggest with this design?
That arousal is somehow affecting performance.
Right, okay, so we can put it that way, right? Our main effect of arousal is just saying that collapsing across task difficulty or ignoring task difficulty, performance differs at least some level of arousal, right? This is basically just a one-way ANOVA because I've got 3 levels. Here is easy, right? Because I've only got 2. Either one's bigger than the other one. There's no other way that can turn here, what we've got, because we've got 3 levels to that second factor, there's a lot of different ways that could turn out. This main effect is just saying that collapsing across task difficulty, arousal differs across low, medium, and high levels, or performance differs across low, medium, high levels of arousal, somewhere in there. Okay. All right, and then we have an interaction. Okay. CJ, what does this interaction tell us?
It tells kind of what's going on. Overall, it depends on both the difficulty and the arousal.
Okay.
Let's see. So, as the task gets difficult, I don't know, this is tough.
Okay. And this starts to get a little bit tricky. At this stage of the game, all we want to do, anytime you see an interaction effect, and burn this into your brain, like, it's going to be the same thing we work on in next semester when we're talking about moderation, anything like that. An interaction just says the impact of one variable on another is dependent on another one, right? So in this situation, yeah, right. So, and Alicia, how do we visually see that there's an interaction going on here? Based on this graph, how we would probably guess that there's an interaction? How do I guess what's telling me that there's likely an interaction in this analysis?
Looking at the high category, the higher or the easier the task, the higher the arousal, the better the performance.
Okay, so we want to be careful. We don't want to cross too many factors here. Yeah.
Can I come up and draw on the board?
You can just verbally say it.
So the pattern is such that on easy tasks, there's a linear relationship. However, when we increase the difficulty of the task, so on task difficulty, first increases and then decreases in terms of overall performance.
Right. So again, we think about this as non-parallel lines, right? If we were to take a point to each one of these bars and draw a line in each one of these, we have a linear function. So the relation between arousal and performance for easy tasks looks to be linear, right? Like this just goes right there. However, we get this parabolic response for difficult tasks where it looks like medium levels of arousal are optimal. If we're too low, we're not doing so great. If we're too high, we're not doing so great. But again, if we were to sort of draw a line here, we've got non-parallel lines, right? And that's going to be telling us that we have an interaction effect. The impact of, and there's a couple of different ways we can talk about this, right? We can talk about arousal impacting differences in performance on easy and hard tasks, right? So we would say that arousal impacts the effect of task difficulty on performance. That would be one way to talk about this. Or we could flip it around, right? Because these interactions are interchangeable. We could talk about task difficulty impacting the effect of arousal on performance. Either way, perfectly fine. How you decide to talk about these designs is going to be largely driven by your hypotheses, your conceptualization, and things along these lines, right? Generally, what we're thinking about here, and sometimes it would be determined by how your data are turning out, but most of the time, we have some idea about sort of established differences, right? We say these two groups are different from one another, right? This is pretty well known. However, there's this other factor that we want to come in and take into account. And so what we'll often talk about is that other factor that's maybe a little bit less explored as being sort of the moderator, right? And so we would say as well that this difference that everybody knows, that's been sort of demonstrated time and time and time again, actually is dependent on this other factor, right? And when we pull this in, then the pattern starts to look a little bit different. Okay. So we've got our significant effect of task difficulty, significant level of arousal, or interaction, right? Now, because the influence of arousal on task difficulty, or the influence of arousal on performance, or the influence of difficulty on performance is based on sort of the other factor, we say that these two factors are interdependent on one another, right? And so in this case, what we would probably do is just ignore that main effect, because those are no longer main effects. They're conditional effects. In the presence of an interaction, our main effects aren't main effects anymore. They're conditional effects. Because what we see is that from the results of our statistical model here, we see that the effect of arousal on performance is dependent on task difficulty, right? Or conditioned on task difficulty, okay? Conditioned just means dependent, okay? Write this down somewhere. If you're not writing this down, you need to be writing this down somewhere, right? Or we could flip this around. We could say, with a significant interaction, we would see that the impact of test difficulty on performance is conditioned on or dependent on arousal level. We can talk about it either way. It just means that this effect is dependent on some third factor. Okay? And so within this, what we're going to want to do is we're going to want to probably not talk about those conditional effects or focus on those so much. We're probably just going to jump right into the interaction and start talking about that. Because in the presence of that interaction, Chris, if you said, well, what's the impact of task difficulty on performance? I would say, I don't know. What's a person's level of arousal, right? Or if you say, what's the difference, what's the effect of arousal on performance? Okay, depends on whether we talk about difficult tasks, we talk about hard tasks. I can't really tell you that, right? And so in this example, probably what we would be doing is just not even in the presence of that interaction, just kind of skip over and just start talking about sort of starting to break that apart or coming up with a plan to pull that apart. Okay? And as we talked about before, we don't always have to. If that conditional effect is still important, right? We've talked about smoking behavior on health outcomes, right? We might find an interaction of smoking on the relation of smoking behavior on health outcomes is dependent on genetic risk or something like that, right? Or age or something like that, right? Let's say we have an interaction of age and smoking behavior on health. At the end of the day, smoking behavior is bad. Smoking is bad, it's associated with negative health outcomes. So in that case, we might want to at least mention that on average, collapsing across age group, people who are smoking have worse health outcomes than those who aren't. However, what we see is that in fact is conditioned on age such that these outcomes look to be worse for older individuals than they do. So we're probably not going to have a lot of 20-year-olds with chronic heart disease or lung disease or things along those lines, right? So we're seeing a bigger impact in older age, but irrespective of it all, smoking looks to be bad on your behavior, or smoking looks bad for health outcomes. So what it really requires you to do is think about, okay, what am I doing? What are these data saying? And then is it important, or is it worth my time to go through and talk about these conditional effects? Again, these are, in the presence of an interaction, these aren't main effects. These are conditional effects, okay? Now, and tradition would say that we just jump straight to the interaction. That's oftentimes what we'll do, but if there's reason to go through and you make an argument for why it's important to interpret these, you can go ahead and do that as well. Questions on any of this? Yes?
Is it possible to have an interaction effect without one of the main effects being present?
Absolutely, right? And this happens all the time. We talked about this again too. Sometimes people are like, well, you can't interpret an interaction effect in the absence of the main effect. It's a fundamental misunderstanding of what's going on. Within these designs, the effect of A and the effect of B and the effect of AB independent of one another, right? So I can go through. Okay, yeah, we go back to and take a look at here, right? Here we have a main effect of factor A. These two are different, no B, right? But no interaction here, right? Here we can have a main effect of factor A and factor B, 20, 30, 15, 35, but there's no interaction, right? At levels of A, if we go to 10 to 20, or 10 to 30, we jump up 20, 20 to 40, 10 difference here, 10 difference here, no interaction going on right here. Same thing. Difference in B across A1 is the same. Difference in B across A2 is the same. Difference in A at B1 is 10. Difference in A at B2 is 10. So we got a main effect, main effect. Here we have an interaction with no main effects, right? So if I look at difference of A across A, difference in A1 and A2 collapsing across B, 15 and 15, there's no difference there. We look at differences in B collapsing across A, 15 and 15. We don't got anything going on here, right? But if we look at our cells, we see something very different going on, right? We've got a cross effect. For at level 1 of A, as we go from B1 to B2, we have a 10-point increase. At A2, as we go from B1 to B2, we have a 10-point decrease, right? So we have an interaction effect here in the absence of main effects. This can happen, it does happen fairly regularly, okay? It just means oftentimes what it means is that that interaction effect is just literally a cross effect, and so it cancels out the main effects, and what you have there is actually a really interesting interaction effect, right? Because if we were just looking at A, we wouldn't know, or looking at A, wouldn't see any difference. Just looking at B, we're not seeing any difference. Back up, these things are sort of not dependent on one another, but what we're looking at is that interaction, and that's seeing that the impact of A on my outcome does depend sort of importantly on level of B. Okay. How are we feeling about this? Interactions are kind of a hard thing to wrap your head around. We'll go through examples to make sure that you're up to speed with stuff, but questions about this right now? Okay, cool. So again, so this is, if I just say, hey, there's an interaction of A and B, tell me what that means. You should immediately say, well, the effect of A on outcome depends on B, but the effect of B on outcome depends on A. That answer is correct for any interaction term, or any interaction effect that you could be presented with in regression, means-based analyses, things along those lines. And it's a nice conceptual understanding of what's going on with this stuff. Okay. So just because, and this is actually will be relevant for next semester, but also some stuff that we'll touch base briefly in here, thinking about ANOVA models in terms of a GLM approach, or generalized linear model. ANOVA is just a special case of regression. Nothing is a mathematically equivalent. There's nothing that I can do in a ANOVA setting that I can't reproduce in a regression. They're the same thing, right? We just think about things a little bit different. So remember that with our one-way ANOVA, what we have is we start out with sort of the grand mean of everybody, right? This is where everybody starts. And then we just make an adjustment here based on what group they're in, right? So if we have differences in alcohol use across freshmen, sophomores, juniors, and seniors, right? What we start here with is just overall mean drinking behavior in the overall sample. And then what we've got here is just some adjustment that's made depending on sort of what class they're in, right? So freshmen, if we say freshmen are drinking more, maybe, then we just say, so for if it's in group J is freshmen, then we have an increase, so we add to the grand mean. If it's, say, seniors, maybe they're drinking less, or sophomore or juniors maybe, so that it's drinking less, sort of drop down. If seniors and sophomores are drinking about sort of the same as the average, then sort of this is 0 for them. So we're just making adjustments, plus an error term. This is the specific error term for Tamara's drinking. How far Tamara deviates from her group level is just tossed in there, okay? Factorial ANOVA, same type of thing, we're just adding on factors, okay? So you start again, once again, with, so score for person X, score X, outcome X for person K at level I of factor J and level factor I of level A, factor J of factor B. This is just sort of the individual score. This is just some person's score, right? Anybody in the sample, this is just predicting their score, right? And to get there with our factorial model, we would start with the overall mean. This is everybody, right? So the grand mean of everybody there. And then we're going to make an adjustment for factor A, where they are in there. We'll make an adjustment for factor B, whatever factor B they belong to. Make an adjustment for the interaction, and then just whatever error terms or that person's deviation from their individual cell, sort of tacking that on here, right? But what we've got is an additive model where we start out with the grand mean, and then we just make adjustments, right? So again, if I'm looking at the impact of, let's say, sex and class status on drinking behavior, okay? To go through and predict any person in our sample's level of drinking behavior, we would start with a gram mean. Factor is sex. Okay, let's say, all right, is this person a male or a female? Right. Well, they're a woman. Okay, so drinking behavior lower in women. Okay, so let's, what's that?
I think so in college students.
Okay, so let's say, okay, here's gram mean, here's everybody in the sample, but this person's a woman. So we're gonna sort of make our adjustment down a little bit, right? And then we're gonna go through and say, okay, what about the effect of factor B? Let's say factor B is class standing, right? Well, this young woman is a freshman, right? We know that freshmen have systematically higher levels of gram, so we're gonna crank that up sort of maybe right here, right? And then we have the interaction of those two that says, in addition to the unique effect of gender and class sizes and interaction of these two, and so then we're going to make a sort of adjustment there, right? And then what we do is just say, sort of however far that person ends up deviating from their individual cell, that's sort of my error term, so that the flux right there, right? So what we're just doing is we're starting with the mean and then sort of making adjustments up and down in an additive model. And this is how sort of the basic approach for our general sort of linear models in terms of predicting outcomes for certain individuals. Okay? And if our model is perfect, if class and gender does a perfect job in predicting drinking behavior in undergraduates, then this is going to be 0, right? That my sort of drink level is completely determined by my gender and my class status. That's not the case, right? And so our error term can actually be sort of quite large. Well, what we're expecting is that error term across individuals is going to be kind of normally distributed. In general, sort of we'll average around 0, but so we're going to have some deviations there. Okay. So this is just saying that basically anything, and again, remember that t-tests, ANOVAs, this is just a special case of regression, right? We can analyze any of these models within a regression format, and sometimes there's going to be times when that's advantageous. ANOVA is nice because people understand it. Like, oh, so mean-based difference. Mean-based difference is kind of easy to think, like, oh, this group is bigger than this group, right? But the underlying math is just a generalized linear model, and sometimes there are going to be cases where it's going to be, we can do things within this framework that we can't do with a straight up, like a classic, like old school, like 40s, 50s experimental type analysis in terms of group-based stuff. All right, so don't worry about this too much. This is just kind of a precursor, give you a heads up to put it, plant that seed when we get into next semester and maybe some stuff we'll talk about. All right, cool. Another thing to think about in terms of our factorial designs is our factorial designs tend to be more powerful than our individual one-way designs, okay? And what ends up happening is when I start adding in additional factors, it starts accounting for variability within my data. What ends up happening is I start to do a better job of accounting for sort of differences in sort of whatever it is that I'm measuring, okay? These additional factors and interactions, you can kind of think about these as kind of covariates in your model that start to increase the power of your test, okay? So let's go through, let's say we have a study looking at emotional arousal, okay? Continuous, sort of calm to excited, in response to fear, amusement, and anxiety, and anger eliciting stimuli. Okay. Christy, tell me what is this? What is this? How would I analyze this study here? What am I talking about here?
This would be one.
Yep, this is on. Someone shouting or something like that. What's going? Where's that at? What's that? Is it? Wait, hey, pipe down. Okay. Distracting me. All right, you're absolutely right. This is going to be a one-way ANOVA, right? So we've got three different film conditions. We've got fear, amusement, and anger, and we're looking at the impact on emotional arousal, right? And likely what we would find in this one-way design, we would probably find an omnibus effect of film type, right? That we see that whatever film stimuli that we've grabbed probably have level of emotional arousal probably differs to some extent across these films, right? But is film going to be the only thing that determines sort of people's level of sort of emotional activation in this case? No. There's probably other stuff that goes into it, right? But if I haven't modeled it, where does that variability go? Yeah?
Error?
Error, exactly. Because it's variability that's not attributable to the film, it's just individual differences types of stuff. And so this is, that variability, it's not random error, it's systematic variability, but if we haven't modeled it, it's going into my error term. And if it's going into my error term, what does that do to the power of my test? Decreases it. Remember, because your mean squared error, so all this is going into the denominator of your F, and as that number gets bigger, what happens to my F statistic? It gets smaller, right? So what if I go through and I do a second study, and I've got the same thing. I'm interested in looking at the sort of emotional arousal response to some different films. But this time I have film condition, sex, and then interaction of those two. Okay. If there is, in ratings if there are systematic gender differences in response to these three films, now I've captured that within this within this sex factor, right? And so now instead of that variability getting dumped in the error term, I've modeled it, I've captured it here. And if there's an interaction between the film and gender, right? So maybe men are maybe overly responsive to anger, more so than the women, and so then the women are sort of thinking funny films funnier than the men do, right? Then there could be an interaction for that too, and then that's going to get captured in here, right? So if, all this stuff, this was still going on in the first study, right? But in my factorial design, now I've got an effect for sex and interaction there. What's happened to my error term here? It's gotten smaller, right? Because that stuff that previously got dumped in here is now being accounted for as an actual effect. And what it's done, even if sex and the interaction don't reach traditional benchmarks for statistical significance, variability due to these things probably isn't zero, right? And even if it's not zero, and even if it's sort of even a little bit, it's systematically reducing my error variance here, making my whole design more powerful, right? Because this is the same error term that's used to test this, to test this, to test this, and the smaller that is, the more powerful my test. So on average, we find that our factorial designs tend to be more powerful than our just one-way analyses. Questions about this? So this is an important thing, and same thing happens in regression in terms of thinking about developing your theses, right? A lot of time what's that?
I was recently, that's what I was late for. I was just talking to Kyle about this.
Okay. Well, this is one of the things, right? When we're doing our between subject design, sometimes the types of questions we have, if at all possible, use a repeated measures design, right? Because that's going to be intensely more powerful than our between subjects design. Sometimes we can't. The things that we're interested in, we can't model as a repeated measure. Let's say I'm eating pathology. I can't assign you to do eating pathology and then don't do eating pathology and let's see what happens, right? That's going to be a between subjects design. But depending on what our outcome is, if there are other factors, covariates, things like that, that we can sort of start to model in, that starts to reduce that error variability, right? And this is where understanding your field starts to become really important. You say, well, I'm interested in looking at these things. But I also know that this other thing has a strong association with the outcome. And this other thing tends to be kind of unrelated to the things I'm going on over here, but I should probably account for this other thing. So that it included as a covariate or something along those lines. Because what it's going to do is it's going to shrink down that error term, and it's going to make the test of the things that I'm actually interested in much more powerful. So Layla's design, she's looking at empathy across individuals, the relation of PTSD symptoms with empathy, right? And looking at some interactions, moderation stuff going on there. Those interaction terms, you need a lot of people in order to go through and test that. I think those sort of, you need like 400 people to adequately power just an interaction term. Yikes, right? Well, what we can do is we can start saying, okay, what other things are associated with empathy that are going to be relatively unrelated to PTSD and to the other stuff that she's looking at, right? And if we can find those things, right, the stuff that if I'm saying, here's my outcome, right? And then here's the thing I'm wanting to look at, X1, right? this is still a pretty big error term. There's a lot of stuff that's not in my outcome that's not being accounted for by what I'm wanting to look at, right? If I can find a couple of other things that are biting out chunks of the total variability that are unrelated to this, so the correlation between these things is 0, right? But now, if I'm looking at my error term, that's going to go through and sort of be the denominator of my tests, is that, right? It's much smaller, right? And so what I've done here is, 1, I've reduced my error term, and 2, I probably have a better specified model, right? I'm including things that account for whatever my outcome is, and sort of just not just leaving it up to chance. And so all of a sudden, this effect here that I'm actually interested in becomes much more powerful, right? The denominator of that test statistic is getting much, much smaller with sort of the inclusion of these different covariates, okay? Now, what you don't want to do is I say, okay, well, I'm looking at, let's say interpersonal functioning is my outcome with PTSD, right? But I want to sort of increase this up. So I need to, what else is associated with interpersonal outcome? I go depression. I'm going to covariate for depression. Wrong, wrong, wrong. Because what depression is going to do, depression is just going to do that, and now all of a sudden, my effect of PTSD now isn't, I just swamped out my ID, right? So you don't want to include as covariates things with strong correlations with your sort of main variable, because you're just going to swamp, everything's going to swamp itself out, right? But if you can think about what other things are associated with my outcome that aren't related to sort of my main effective interest, those make very, very, very good covariates, okay? And so in general, this is the type of thing that ends up being causing our factorial designs to be more powerful. And so again, this always comes into study design and planning and things along those lines, right? Knowing whatever phenomena it is you're interested in studying, say, okay, this is my question. What other things are important to think about and accounting for sort of this? And we don't do this enough, right? We're like, well, I got this thing. I want to see how it relates to this thing, and then call it good, right? Sometimes if we're using existing data, that's what we're stuck with. But if I'm planning a study to put together and say, okay, well, this is the thing I'm interested in, but here are other things that I know from the literature are associated with my outcome, so that are important, right? And these are things that are often also kind of unrelated to the thing that I'm interested in. You should measure those things and control for those things. It's just going to make for a much more powerful design. And our goal as researchers should always be not to have 500 people in our sample. We can collect 500 people, cool, right? But if we don't need to, that's awesome, particularly in like experimental designs and things. All right, questions on sort of power issues here? All right, effect sizes for our factorial ANOVA. Eta squared still works. We still calculate eta squared. Eta squared is easy peasy. It's just our sum squares of our effect over sum squared total. We interpret eta squared as a proportion of variability in these data uniquely attributable to whatever the factor is. That's cool, right? Again, what we're doing here is we're looking at the proportion of variance in this sample of the total variance in the sample that's attributable to our effect. Okay? So the interpretation of eta squared isn't any different than it was previously in our one-way ANOVA. Okay? But again, as we talked about before, eta squared is positively biased effect, right? And so we have some concerns because the sum of squares effect for any factor that I include in my study, Alicia, is it going to be exactly 0? Not going to be exactly 0. It can't be negative, so it's going to be something, right? Eta squared is never going to be exactly 0, and so even if the population effect is 0, the number that I get is not going to be exactly 0, so we talk about this as a positively biased estimate. So again, eta squared is nice in terms of thinking about a descriptive statistic, but it's going to be positively biased, and so we want to be careful with this. Other thing when we switch over to factorial designs is we find that our eta squared is going to start to systematically decrease with the number of effects in our design. Okay? Now in the perfect world, if I've got perfectly orthogonal, all my factors are completely randomized experimentally controlled things, this starts to become less of a concern because if I randomize you to condition A, condition B, condition C, like your status should not differ across the, so there shouldn't be, A, B, and C should all be uncorrelated with one another, right? And if that's the case, then we're doing okay. But a lot of times we're using these designs to look at existing things, right? So looking at gender, right? And class status, right? Gender and class status probably aren't completely orthogonal. Who's more likely to make it into sort of through university career, men or women? Probably women, right? In terms of sort of going through, and so then because of that, as soon as sex and class status are related to one another, what it's ended up happening is that sum of squares effect, this is just getting the stuff that's unique to biological sex, and this is just the stuff that's unique to class status. Anything that overlaps gets sort of tossed into, so it doesn't, no one gets credit for things that are overlapping here, right? And so what happens is, let's say that my sum of squares effect and sum of squares total is 100, right? And let's say it's 20 in my one-way ANOVA, right? So here, eta squared is going to be 20 over 100, right? Well, let's say I added another effect, right? So I'm going to go through a factorial design, so I add something else in, right? And these two factors aren't completely correlated zero with one another, right? What's going to happen to my sum of squares effect? Part of sort of this effect starts to get chipped away by sort of overlapping stuff. It's going to decrease, right? So now, my second factor, let's say it's 18. What happened to my eta squared? It got smaller, right? Let's say I added a third factor. It's kind of overlapping. Let's say, so this third factor does kind of overlap quite a bit, and so now this is 11, right? So what ends up happening in my factorial designs, if I'm comparing eta squared for it, and let's say this is an effective class status, right? If I look at the effective class status on an outcome, on drinking behavior, in just a one-way design, that eta squared is probably going to be systematically larger than if I start accounting for, let's say, sex, and let's say high school drinking, whether or not I drank in high school, yes or no, sort of back there. So these are all going to be kind of pre-existing things that aren't experimentally manipulated, and so there's going to be some overlap. And so what we see as a concern with our just straight up eta squared is that this effect will start to be, we worry about it being comparable. So I've got an eta squared from a one-way design and then a factorial design, and I'm seeing differences. It's hard to say that those two things are comparable, okay? And so again, eta squared being nice because it had an easy interpretation. We're saying that for these data, high school drinking behavior accounts for 15% of the total variability in college drinking behavior. Cool, that makes a lot of sense, right? But the problem is if I start comparing that with more complex designs, it's kind of an apples and oranges comparison here. Okay? So what we have is we have partial eta squared, okay? Partial eta squared is looking at the proportion of residual variance unaccounted for by other factors, okay? This is going to be something we're going to talk about a whole lot when we get into next semester in terms of regression. But if I'm talking about residual error, okay, I'm saying that here is total piece of pie, right? And my total variability might be V, and then I have, say, factor A, right? And then let's say I've got factor B here, okay? If I'm looking at factor A here, right, now I want to calculate eta squared for factor A. I'm going to take this here as my sum of squares for effect divided by what? For eta squared. The total, right? The big circle. And the same thing if I want to go through and I want to take a look at eta for factor B. We've got this divided by partial eta squared. This partial eta squared is just looking at the proportion of variability attributable to our factor over the stuff that's unexplained by other things, okay? And so if I'm calculating partial eta squared, right, what I'm doing is I'm going to take my sum of squares effect, and I'm going to divide it by this plus just my error term, okay? And so what ends up happening, Chris, to the denominator of my effect for partial eta squared relative to eta squared? It's smaller, right? Because this doesn't count, right? Partial eta squared says, well, this amount of variability is attributable to other factors, so we're going to take that out, right? And so what partial eta squared, when I was talking about the residual variability unaccounted for by other factors, we're saying this is accounted for by B, so we're taking that out of the picture. And so of what's left over, after we take B out of the picture, of the residual variability, of the stuff that's left over, how much of that is accounted for by this other factor, okay? And so what ends up happening is that as I start to add into if the concern is for eta squared, right, that as my design gets bigger and bigger, piece of the pie is still the whole pie is still a whole pie, right? That still ends up being the denominator, but my numerator starts to shrink up, particularly if there's overlap in my factors, right? But for partial eta squared, I'm still looking at my overall effect, but if it's getting cut away, as the more I add other factors in, it's also chipping away on the sort of my residual variability. The total variability I'm accounting for starts to increase, and so this is just my sum of squares effect over my residual variability. So what's left over after I sort of take out all those other factors, right? And so what we end up doing is we end up getting partial eta squared is going to be, how's partial eta squared going to relate to eta squared?
It's larger.
What's that, tomorrow?
It would be larger.
It's going to be larger. It's going to be systematic. It can never, partial eta squared can never be lower than eta squared. They can be the same, right? If my factor B truly has zero correlation with my outcome, then eta squared would be equal to partial eta squared. But what we can do is we can go through and start to compare partial eta squared across different studies, and that being a more comparable effect size. We see partial eta squared also central in the calculation of power. Okay, so when we're going through and keep doing power analyses, partial eta squared is the statistic that you'll be using. Conceptually, it's kind of more problematic. It's hard to say, okay, so I'm going to say that sort of my factor, this is the proportion of residual variability in the outcome that's attributable to this factor. I don't know, residual variability in my outcome is hard for me to think about because total variability, I can think about that, right? Residual variability kind of depends on what else is kind of in there. So it's become a harder thing to apply or sort of wrap my head around in terms of conceptually. But wanting you, when we're going through and making these interpretations, sort of recognize that what we're talking about with partial eta squared is we're talking about the variability, total variability in my outcome that's left over after I pull out all my other factors. Okay? So you'll often see the formal effect size for power analyses is not eta squared, it's an F statistic, but eta squared and F have a direct correlation, and so we should jump back and forth to do that when we're working on power analysis stuff. So questions about eta squared, you have that under control. You were working with eta squared in this last set. Questions about partial eta squared? Yes?
Are the interpretive standards for that more like F?
No, they're the same. Interpretive standards for eta squared and partial eta squared are identical. So
Okay.
you can use those. That's a good question. Thank you. And same thing for the omega statistics we'll talk about in just a moment. Other questions? Okay. So that's eta squared, omega squared, or excuse me, eta and partial eta squared. We also have omega and partial omega that we can talk about. Again, remember that omega squared is preferable and that it tends to be a less biased estimate of the population effect. So if we're going through and we're talking about eta squared and partial eta squared is a good descriptive statistic for these data that I'm looking at right now. It looks like factor A is accounting for this proportion of the total variability, or if I'm talking about partial eta squared, say this factor is accounting for X proportion of the partial or residual variability in my outcome. But it's a biased population estimate. It's going to be too big. Omega squared, better, because we can go down through and it's going to be a better population effect. So when we're talking about omega squared, making interpretations of omega squared, being sure to indicate that we're talking about this as a population estimate as opposed to sort of what's going on in these data. Limitations of omega squared, though, as we start to get in away from omega squared into partial omega squared, the calculation starts to depend on the design and sort of what's going on. It starts to get more complicated with stuff. And so anytime anything starts to become more complicated, people don't want to do it, so you don't see people using this a whole lot, even though they should, because it's a better estimate. Other thing with omega statistics, it's assuming a balanced or nearly balanced design. That was one thing. So for 2 of the 3 problems in this last set, the design was really unbalanced, so you should probably be talking about and interpreting eta squared as opposed to omega squared. If you didn't, that's fine. I'm not going to take any points off. We'll mark it on your thing, right? And that's also kind of not fair, because I told you omega squared was better to interpret than eta squared, which it is, assuming that you have a reasonably balanced design. If your design's all the way off base, then you should probably stick with eta squared. This is just I'm not going to trick you guys and then take points off, but sort of just have that in your head. So the thing is, as we're going through and calculating omega squared and partial omega squared, sort of the general idea is the exact same as eta squared and partial eta squared. It's just going to be a better population effect, because it's going to start to account for different sources of error. So again, if you look through Howell, depending on what type of design you have, so this is how you could go through and put together components for a 2-way factorial design. Formula are going to be different if you have like a 3-way factorial design. It starts to get pretty involved with stuff. So if you see something like this in text, this is just kind of what it's talking about. This formula here will pretty much get you the same direction, okay? Particularly for partial omega squared. Partial omega squared in Howell's procedure will give you the identical effects for unbalanced designs. But what we've got here, PowerPoint likes to screw up with screw my notation over here, but for calculating for a factorial design for omega squared, you're taking the degrees of freedom of whatever effect you're interested in, multiplied by the F statistic for your effect minus 1, that should be right, over degrees of freedom factor A times F for factor A minus 1 plus degrees of freedom for factor B times F for factor B minus 1, versus however many factors you have in your design. Okay. Partial omega squared is actually easier to calculate than omega squared. Just degrees of freedom of effect times the F for whatever effect you're interested in minus 1 over degrees of freedom of effect minus F for the effect minus 1 plus the total number of people in the sample. All right, easier way to go through and calculate that there. So again, I went through one of those handouts. In my own personal journey and trying to figure out sort of what's what and how to sort of present sort of formulas and things along those lines. I mean, this is how I learn to keep things under control. It is, yikes. These are like just my notes that I put together and sort of tried to sort of keep this all straight in my head. I just took that and put PSYC 50, 60, 5300 on the top and then called that a handout. But that's what I can do, is just like take my own random scribblings and just go ahead and throw a title on the top, and now it becomes official. This gets into some stuff with repeated measures as well, but I think kind of a nice resource with stuff is if you're having trouble sort of thinking about how do I talk about these things, or this is the other thing, one of the things that makes it's hard for people to systematically include effect sizes in their research is it's hard to find a single resource that has a comprehensive treatment of sort of this stuff. If I look in, you'll see on what the second page across 6 different sources, I've got 6 different formulas for an effect size. And most of them are mathematically equivalent, but some of them aren't. And so it's just like going through and trying to figure out, punching numbers in, saying, okay, so if this and then that, trying to go through and figure this out. So it ends up being, I mean, I've got 7 different ways to calculate the same effect. Most of them are the same. Looks like there's errors in a couple of them, right? It can be super, super confusing. So for the stuff that we'll do, if you do this for between subjects factorial designs, this will probably get you where you need to be. But just remember, the idea is that omega squared statistics are nice because they're a better population estimate. They're still a little bit positively biased, but nowhere near as positively biased as eta squared statistics. The caveat there is that they take a little bit more effort to go through and calculate. Unless you have a program that does it for you, then it's easy. Other thing too is you should probably be relying on sort of reserving calculation of this stuff for designs that are relatively balanced. And if you have a design that's just not balanced, then we just fall back on eta squared, and that's fine. Just recognizing that that's more of a descriptive statistic than anything else. Questions on this? All right, so same thing for calculation of upper and lower bounds of partial eta squared. The same stuff as we did before. I don't know that I'm actually going to have you work on that at all because I haven't found anything terribly. Like, we're rarely interested in sort of upper and lower bounds of an omnibus effect within stuff. But if you ever have occasion to do it, this is how you do that. So again, just to pull things together, eta squared, omega squared. These are going to indicate proportion of total variability attributable to a factor. Okay, so accounts for all components variation. It's going to sum to 1. It's going to be all of this stuff here if we're talking about eta squared, omega squared. For our factorial designs, going to be considered a conservative estimate, and it's also going to be always going to be smaller than the partial coefficient. Partial effects, eta squared and omega squared. This is the proportion of residual variability after accounting for other factors. Okay, so after we suck out all the systematic variability due to other stuff, we're saying that this is of what's left over. This is the proportion of what's left over, which is attributable to our factor. If I sum up all of my partial eta squareds in my design, it's not going to add up to 1 because it's using different pieces and parts. We see that eta squared, partial eta squared, useful for comparing across different designs. Caveat there is it doesn't do a good job of accounting for repeated measures. When we get into next semester, we're talking about repeated measures, mixed factorial designs, where you have a mixture between within subjects factors. Then we need to start thinking about a different type of effect size, generalized eta squared. A little teaser, right? You guys would be excited. Like, I can't wait till February, March to learn about it.
Again?
What's up?
We take stats again?
Yeah, you do, man. This
What?
What?
No, I'm just kidding.
Okay, I was like,
Terry yesterday was like, yeah, you always look confused.
I was like, oh, buddy, do you not know that you have me again next semester?
No, I do.
Right, you're excited about it, okay? But when we get into our repeated measure designs, we're going to have to use a slightly different statistic in terms of something that's going to be comparable. But our eta squared, not our omega squared. Well, probably our eta squared is going to be what we're going to be using to go through and calculate power for specific effects. All right. Questions? G power. Look at F, ANOVA, fixed effects, special main interactions, a priori. So you go through and determine. If you hit determine here, it'll calculate your F for you. You say, here's my partial eta squared. Drop that in, calculate it, calculates for you, put it over there. Error probability, this is your alpha level, power. Numerator degrees of freedom, this is just going to be your degrees of freedom effect. For main effect, it's going to be the level number of levels -1 for the interaction, so we'll just do that. Number of groups is just going to be how many cells you have in your design, and then that's just going to drop out your run your power analysis there. So again, for simple designs, G-Power being a decent tool. Okay. Questions about where we're at with stuff? Okay, cool. Let's open up. This, you have a data set. So grab your sheet. The 2x2 ANOVA screening for expressive behavior. And open up that the data set, the expressive 2x2 PSYC 5060 2x2 ANOVA expressive behavior data set, and sort of pop that open. Okay. So while you're doing that, again, this is, I don't know, you guys are probably about half over film designs, but sort of my thought is that we're using sort of variations on the same set, sort of giving you sort of building on sort of just general design and kind of what's going on. Here, what we're interested in theory, is the impact of expressive regulation on physiological activation and subjective response when shown some sort of emotionally provocative film. In this study, we randomized students to view one of two different affectively balanced films. So people are either randomized to watch a sadness film or a humorous film, under instructions either to inhibit the external expression of emotion or to watch the assigned film naturally. Okay? So tomorrow, what type of design are we talking about here?
One-way ANOVA.
What's that?
What type of design?
Yeah.
ANOVA.
ANOVA, okay. So, but what's the structure of that ANOVA design?
One-way.
What's that?
Like a one-way.
Okay. Well, we've got people assigned. So we've got kind of two different conditions, right? People are assigned to watch a humorous film or a sad film, and then they're also randomized while they're watching that assigned film to either just watch it naturally or inhibit the expression of emotion.
2x2.
So we got a 2x2, right? So we've got a 2x2 factorial design, right? And this is a true experimental design. We got people came in and we randomized them to each one of these things. But we're saying prior to evaluating our primary outcomes, reviewers requested investigators conduct a manipulation check to assess the validity of the expressive manipulation. Okay? So we're saying in this hypothetical scenario that I got a response from the reviewer that said, well, just because you told people to inhibit their expression, did they actually inhibit? Did they do what they were supposed to do? Right? Which is a reasonable request, right? So maybe let's go through, and what we're going to do is, luckily in this study, what we ended up doing is all their assessments got recorded, and then what we did is had someone go through and code behavioral expression of each one of these individuals and rate global expression on a 1 to 5 rating. 1 being no expression at all, 5 being completely through the roof in terms of expression, right? And so the idea is, what we want to do is make sure that individuals sort of looking at expressive behavior across film and instruction condition. And our hypothesis is that individuals instructed to inhibit expressive response will evidence lower ratings of global expressive behavior. Okay? But we've got a couple different ways things can go, right? We can have an effective film, we can have an effective expression, right? But what we're really interested in within this design is we want to go through it and make sure that for those individuals who were told to inhibit expression, that they're doing that irrespective of sort of what film they're watching. Okay? So again, we're going to null alternative, sort of do all the stuff that we typically do. Okay. Questions about kind of the setup here, what we're trying to accomplish with these analyses. Okay. With these designs, okay, and I cannot emphasize everybody to look at me in the eyes right now. All right. Don't jump in the middle of these without having a good game plan for what you're wanting to do. You will spend more time trying to slam around and figure out what the hell's going on with stuff than sort of on the front end saying, okay, what are my objectives? What are the hypotheses? How do I go through that? You want to have a game plan for approaching these analyses before you just kind of jump in the middle and just start doing stuff. It'll make your life so much easier You have to make sure that you're very, very clear on what the design is, what's being measured, and then what the hypotheses are. I can't give you a set of rules to go through and research question, and it's going to depend on the effects. And so you're going to feel like you're lost out at sea if you don't have a good game plan before you jump into this stuff. So plot it out, sketch it out, say, okay, what do we want to do? How do we tease this apart? What do these effects mean? How are we going to go about exploring this before you jump into stuff? Trust me, it'll just make your life a ton easier. You'll spend a lot less time. It can be kind of irritating on the front end of deck. Oh, sometimes it's just fun to kind of jump in the middle of the stuff and see how it works. But I'm telling you, you'll spend more time doing that than if you sort of take the time on the front end to have a good game plan set up. Okay. So what we're going to start doing here is we're going to go through and start with the screen. Okay. What's nice is that screening for factorial designs is pretty much the same thing as screening for the one-way designs. You just have to go through and account for more cells. All your assumptions are pretty much the same. It's just getting things broken down into individual cells. So for these data, what we've got is we've got a film condition, 0 corresponding to sadness film, 1 corresponding to humor film. We got instruction, 0 equals express, 1 equals withhold, right? And then what I've done, just to save us time in here, is I've gone through and created a condition variable that's going to go through and it's just going to have individual cells, right? So 1, sadness express, 2, sadness withhold, humor express, humor withhold. You'll need to go through it in other sets. You'll need to go through for screening and calculate that on your own. I mean, it's not hard. I mean, what I do in SPSS is I just will sort 1, sort 2, and then just paste in values. It doesn't take too long. Alicia, if you look at status stuff, there's actually just a quick command that'll do it for you. So that's what that's looking at. But for screening, you're going to have to make sure that you have an indicator identifying individual cells. Again, I've done it just to save some time here. And then we have express is just our expressive behavior thing on the back here. So what's the first thing we're going to do in terms of screening? What's step number 1? Check for missing data. I like that. I think that's a good thing to do. So, and I already see one right there. Okay. So we know that I'm going to go through, and because this is an experimental design, I shouldn't have anybody who's missing an experimental group, because that would be bad, but it's possible, right? So those are all good. But if I go through, take a look at my expressive behavior, it looks like there's 3 individuals here who I didn't get behavioral codes for. And so what I'm going to want to do here is, again, with our group-based design, for our missing data, we want to go through and make sure that we are making note of what groups are missing data, so where's our missing data occurring, right? The idea is that what we don't want to do is if we have all of our missingness in maybe like one condition or something like that, that starts to say that those missing data may not be occurring at random. There may be something about that specific condition causing the loss of information. That's going to be an important thing to know, right? But for here, looks like we've got participant 112, 32, and 200, all missing values, right? Looks like first one is 112 is sadness express, sadness inhibit, and humor inhibit. So are we too concerned about systematic missingness? No, right? And if we go down through and take a look, 192, like, are we concerned about 3 missing people? Not too much, right? This is all my dissertation data here, so we did a pretty good job of getting sort of behavioral codes for people here. So what we want to do is go through and somewhere on the sheet, sort of mark down what cases had missing values, what groups they were in, and then once we've done that, we can go through and clear that. And then always never work with your actual data. Save some sort of scrap or screen file. Just saying, if you do this consistently, you will thank me when everything falls apart and you're not actually using the one copy of the actual data that you have. That's going to be bad news bears. Okay? All right. So we've gone through recorded our missing values. What do we want to do next?
Make sure all our data is plausible.
Yeah, we want to make sure everything's within bounds, right? So we're going to go to data, we're going to go to split file, we're going to compare by groups, and what do we want to split the file by, Chris?
I guess condition.
Yeah, condition, why?
That's what we're interested in looking at.
Yeah. Think about this. So we've got a 2x2 factorial design. How many cells do we have? 4, right? And each one of those 4 cells reflects its own individual population, okay? Each one of those cells is kind of its own thing, right? And so what we want to do is an extreme value in one cell might not be an extreme value in that cell, right? Particularly if you think about what we're doing. We're showing people sort of sad films and happy films and looking at expressive behavior, a high level or extreme level of expression in response to a humorous happy film might, or an extreme value in response to a sad film might not be all that extreme for people watching a happy film, right? So we want to go through when we're screening these factorial designs, start to break this up. So what does that mean for our screening as our designs start to get more and more complicated?
Gotta do more.
If I've got a 2x3x4 design, yikes. That's one, you've got to have 1 billion people to populate that, right? And then that's just a lot of folks that you have to go through and do, right? It also starts to be incredibly difficult when you get, if God forbid you actually identify any type of interaction term in that. Yowza, it's just really hard to start thinking about how to pull that apart systematically. So this is one of those things to think about as you're constructing designs, thinking about one, wanting to make sure that you're getting things that you want to get, but then also wanting to make sure that your design is manageable, okay? So we're going to go down through select condition, and we'll go through and paste that, just so we have that here. And then what I'm going to do is analyze descriptives, get expressive ratings, save standardized variables, request skew and kurtosis, continue, paste, cool. We're looking good here, right? So we're going to go through, run the whole thing. All right. Siley, what am I seeing in terms of my descriptive statistics, plausible values, things along these lines? Yep, okay. My minimum statistic is 1, that's low end. Highest statistic is 5, except for sad and headed. So not a whole lot of expressive behavior in response to the sadness for people who are told to restrict their emotions. So all of my values are good, right? So no problems with problematic values. What about distributions within these individual cells?
They look good.
Look pretty good, right? Nothing that's probably too terribly problematic here. Now, remember we're working with, these aren't continuous data. These are ordinal data. It's ordered categorical, right? It's 1, 2, 3, 4, 5, right? It's not a true continuous scale. So we want to keep that in mind. But, so that's good. Anything else from this table that we're at least maybe want to at least make note of and focus on? Yeah, what about the sample size?
They're unequal, but they're pretty close.
They're unequal. Are they super unequal? Not too bad, right? So it's not balanced, but it's probably not too terrible, right? I mean, honestly, for this, I probably wouldn't be worried about interpreting omega squared, partial omega squared for this. So it's pretty decent. What else might be relevant in terms of thinking about the cell sizes here?
In terms of when partitioning the variability, just knowing, or when calculating our effect sizes and knowing what variance estimate we're going to use, with them being equal, we're probably not concerned about the differences in variance across groups.
Okay, so I think that's a good point, right? Because the number one decision we have to make in terms of, and just like one way I know is, do we have problems? Is our mean square error a good indicator of variability across all of our cells? At this point, we don't quite know this quite yet. That's something we're definitely going to want to take a look at What about the size of these cells? Are we happy with the size of these cells?
They're pretty sweet.
Yeah, they're pretty good, right? Remember that our assumption for these group-based designs is not, like I can have kind of wacky, if my distributions, my histograms, things like that look kind of skewed and off, I'm really not too worried about that because remember that the assumption is that on the distribution of sample means, right? And under what two conditions that distribution of sample can start becoming normal?
To increase your sample size.
As my sample size starts to get increased and what? Population is normal, right? Now, for individuals who I tell to, so I show people a humorous film, and I have people to completely inhibit their expressive behavior, and then I rate how expressive they are. Is that likely a normally distributed variable? Probably not, right? Most people are going to be pretty good at it. Some people aren't going to be. Probably going to get some sort of skew with this, right? So the population distribution isn't normal, but as long as I have cell sizes that are of adequate size, that takes care of a lot of that, starts to become robust, right? And so I wanted to go through and thinking about like how big are my cells? Is this, do I have enough people within these to start to reasonably assume that the sampling distribution of the means is going to be reasonably normal within this? All right, so that looks good. What do we want to do next? Yes?
Check your standard deviations, like the upper limits of the standard deviations within each group.
Okay, so yeah, look at extreme values. Yeah. What do we want to do before we do that?
Bar charts.
What's that? Yeah, graphs. So
Graphs.
going through and take a look at stuff,
That's
right?
great.
So what I'm going to do, because I already know this is going to happen, I'm going to go through and sort by subject to turn off that split file, because otherwise it'll. Who's done that? Who's tried to run graphs through Explorer without turning off your split file? Yeah, you get a bunch of nonsense. So we'll just preempt that. Go to descriptives, go to Explorer. I'm going to ask for expression ratings. We're going to look at conditions, my factor list, right? So we're going to split that all up. I'm going to label cases by subject number to make sure that on my box plots, if it's giving me numbers for extreme values, that those numbers correspond to participant numbers and not the position they are in the data set. Plots, I'm going to ask for histogram, turn off my stem leaves, paste that in. Alicia, what are you seeing with this first histogram?
Positive and skew.
Yeah, it's got some positive skew. Now, it can't be that bad because I mean, so my scale is from 1 to 5, so it's kind of limits like how bad it can do. But I would definitely make a note of this graph that it's a nice stepped graph. It's like a Mario Brothers thing sort of going on there, right? So we got some positive skew. What about, Nick, what about the histogram for SAD inhibit for expression here? What's going on here?
Yeah, also positive skew, but
What's that?
it's fine. It's also positive skew, but it's fine.
Yeah, it's positive skew, but it's fine, right? So maybe the thing I would note here is some restricted range, right? So I have basically, this is a trichotomous variable, right? It's 1, 2, or 3, right? Which is not great for our analyses, but sort of probably not something we're going to sort of give up on, right? Chris M., what about for humor express? What's happening here?
It's positively kurtotic.
Yeah, yeah. Or whoops, no.
Negatively kurtotic.
Negatively kurtotic, yeah.
Turtle.
Yeah, it's kind of turtle. It's kind of boxy, right? With most of my values going 2, 3, and 4, right? And tomorrow, what about for my humor inhibit?
Positive skew and bimodal.
Yeah, kind of bimodal. So we've got people at 1 and 2, and then lower levels out, right? But again, if we always wanted to go through and think about like, do these graphs make sense with what I've been asking people to do? Yeah, right? It looks like 4 people who are just allowed to watch this funny film just on their own. This is a modest levels, 2, 3, 4, modest levels of expressive behavior with some people who clearly weren't into the film, some people who thought it was hilarious, right? So that looks all right. But then as soon as I go to it and show people the same film and ask them to inhibit expression, by and large, people were pretty good at it, right? Now, a couple of people still, stuff's cracking through, we broke them, right? But it's, so the histogram is consistent with what I would expect from these data, which is an important thing to think about, right? Same thing if I'm looking at, for the sadness expressive, sadness inhibit, we talk about a restricted range of expressive behavior in response to that sadness film. Does that kind of make sense? Yeah, for the most part, people were pretty good at inhibiting stuff, but we got some stuff breaking through. Here, I think that's probably people. My guess is that we at least made someone cry, which happened, unless it's a sad film. But we're seeing some people, but maybe less expressive behavior here.
What was the film?
What's that?
Was it like Schindler's List or something?
It's clip from the 80s, The Champ, maybe it's.
I thought it was the 70s.
That's like it's late, said like 79 or something like that. It's intense. Like it's an effective film clip, right? Yeah, so look it up. You can pull it up online. And then funny film is from When Harry Met Sally. Yeah, so you're pretty good at eliciting the types of responses that we want to get out of people. Okay. CJ, tell me what's going on with this box plot here.
All of them in general or specifically?
Oh, just sort of in total here.
Well, you can see the positive skew in a few of these, and for the SAD express, SAD inhibit, humor inhibit, that most of the variance is on the lower end of the scale. Got 4 outliers for the humor inhibit. The humor express one looks pretty even.
Yeah.
Pretty good. Let's see, for the SAD inhibit, looks like the median is at the first quartile, and for the humor inhibit, median is at the 3rd quartile.
Yep. Good. So these are all things just kind of wanting to sort of make an interpretation of this. Together, I mean, we'll plot it out together. We can start to sort of get an idea for what's going on across these. For our screening procedures, we're just pretty much interested in sort of individually as we're stepping through. The one thing I would say to watch out for is you can, when we're looking at extreme values, and I would think about these as extreme, but outliers kind of has a sort of connotation to it. Talking about extreme values, I mean, outliers suggest that it's problematic, we need to do something. I mean, on a 1 to 5 scale, do you think a scale, sort of score of 4 is a true outlier that's problematic? Probably not, right? But what you'll see sometimes is in SPSS is because these are ordinal data, so everybody who lands on 4 is all going to be at that same spot. There could be maybe 4 of these or 5 of these that's just being masked in this graph. So if you see these, always go down through and just check your data and say, okay, I see yeah, we do have 3, in the humor inhibit, we have 3 people, these 3 cases that actually are scoring the 4, and then this one is up, just to make sure that you don't miss anything there. Okay. But overall, are we concerned about the distributions for these data? No, looking pretty good. Certainly nothing that would concern us too much in terms of our ability to run these analyses, right? So last thing we want to do is go through and take a look at our z-scores. So for the test of potential extreme values. At this point, this kind of formality, do we have any problems? Are there going to be any scores in here that are going to be hugely problematic? No, right? But we'll just go down through so we can just take a look. So indicate z-express, get rid of that. We don't need skew and kurtosis. At this point in the semester, are you guys getting more comfortable with working with these syntax files and sort of manipulating those? Yeah. Once you start to do it, it starts to become nice, and then you just it starts to come through because screening is a lot of peep replete, so it's nice to have a template. We go through and run this. At least any concerns? Oh, yikes. If you go through turn the split file on again. And run my descriptives. Okay. Alicia, any concern with extreme values here? I mean, you got, for our humor inhibit, so we've got someone who's a little high, sort of exceeding 3 standard deviations. I mean, you might, could maybe make a note of that. But again, in a cell size of 51, are we too concerned about that? No, right? And this is what ends up happening. Again, a lot of the stuff that we do in psychology, we're using scales that have sort of low end to high end. Even if you are high, you can only be so high, right? It starts to help mitigate a lot of the problems with potential outliers versus if we're in sociology or econ or something like that where things can get really, really big. But again, I at least wanted to go through and take a look at this stuff. So in SPSS, what we'll do is we'll go through and run homogeneity variance when we actually run our analyses. But on the back of your handout, again, just kind of, if I were running this screen, is how I might rate this up. Right, we've got 3 cases with missing express scores, identified the case numbers and the conditions or the cells, no evidence of problematic values, tell me how many people in the cases that I'm going to proceed with. We've got distributions, histograms, and box plots for SAD express, SAD withhold, humor express, humor withhold, going through qualifying outliers. Now, when we go through and we take a look at Levine's test, that will come up as possible violation of homogeneity variance. It doesn't look like it's huge, but it's at least getting flagged, suggesting that within group variability across each one of these cells, may be different. Okay, and so this, as Nick had pointed out, is something that we're going to want to think about in terms of planning on how we're going to go through and tease anything apart in terms of our specific effects. So in terms of a summary, say cells in this design are relatively balanced with minimal missingness. Observed distributions for individual cells, generally not normal or symmetrical. However, deviations unlikely to be problematic. For underlying assumptions of the sampling distribution, the size of the respective cells. Right? So again, just saying that, yeah, we know they're not perfect, but at the end of the day, we're concerned about the sampling distribution, the sampling distribution, not the observed distribution. Given the cell size, we're probably going to be okay. Recommend proceed with 2x2 factorial ANOVA with adjustments for Omnibus and follow-up tests, given that we've got unequal variances here. Okay, so we did pretty good within this experiment. We had relatively equal cell sizes, which is nice, right? But just given the nature of the task, I'm not surprised that we have different levels of variability in terms of expressive behavior. So we just want to make sure that as we're moving forward, probably within these ANOVA designs, and for other reasons, it starts to become questionable whether or not we should just be plucking that mean squared error term out of the overall Omnibus table, just using that for tests. And particularly if we have evidence of violation of homogeneity variance, we just want to be careful about that. So, questions about the screening here? Pretty much the same thing as our one-way ANOVA. You just have to make sure that you're breaking out cells. Okay. Questions? All right, cool. Let's go through, take a break, and when we get back, we'll jump into the analysis. Through and wanting to make sure. So we're going to go through and run a formal test on this, but what we want to do is make sure that the data are reasonable to assess using a 2x2 factorial design before we just jump in the middle and start doing stuff. Because it could be, again, remember that when we start to have concerns, if we have our means-based analyses are pretty robust to violations until we start doubling up on violations, right? So if we have unequal cell sizes and unequal variances, then that's problematic. Or we have non-normal data pointing in different directions, right? So if my humor express was negatively skewed, maybe I just got like a super, super powerful, everybody thought it was hilarious except for a couple people, right? So I got a negative skew for expressive behavior for humor express, but my SAD withhold has a strong positive skew. So no one expressed anything except for a couple people who did. Now all of a sudden we've got things going in opposite directions, and that starts to become problematic, right? So we want to go through and start to tease out, like, are these data, when I go through and run this analysis, can I be confident in my inferences based on sort of the results of this stuff, okay? So what we're going to do then, well, we've gone through, consensus is, looks pretty good, except for possible violation of homogeneity variance. So what we're going to go through and do is just go through and run this 2x2 design. So we're going to go to Analyze. We're going to go down to General Linear Model, not Generalized Linear Model, General Linear Model Univariate. Click that. And so our dependent variables are expression. We're going to use film and instruction as my fixed factors. Why don't I drop condition in there?
Because we're trying to figure out main effects too.
Yeah, right. If I were to drop a condition in there, I'd essentially just be writing a one-way ANOVA, and that would make any sense, right? So we don't have anything else here. What we're going to do is we can go down. Let's go to options. We'll request descriptive statistics, estimates of effect size, homogeneity of variance test. We're going to hit continue there. And under EM means, we ask for, just give them marginal means for film instruction, interaction. I'll just drop those in and hit continue. Yeah, we'll call that good. Okay. Hit paste. Go through and run this. All right. Cool. So we got lots and lots of output here. What happened here? Oh, thank you, Sally. You're a genius. There we go. That looks better. Okay, cool. So, want to go through and always want to double check your descriptive statistics you were between subjects factors to make sure that you have everybody in your analysis that you would wanted to have in your analysis. Okay, so it looks like we have 91 people who saw the sadness film, 98 people who saw the amusement film, 94 told to allow to naturally express emotion, 95 told to inhibit the expression of emotion. What do these mean, or what do these sample sizes corresponding to? Number of people in each population, right? So overall, what effects are these giving it corresponding to? What's that?
The interaction.
Okay, not the interaction. These are cell sizes for our main effects, right? So if I'm looking at the main effect of film condition, I got 91 people in one group, 98 in the other group, right? If I want to look at the main effect of instruction, I got 94 in one group, 95 in the other. And then when we get down into descriptive statistics, SPSS does a nice job of providing you with relevant main affected interaction means here, okay? So, Chris, where are my, tell me what my cell means are in this descriptive table.
Are they in the total?
Are they in your total?
I sure hope so. I'm not sure. Isn't how the, like, express would be, oh, the cells, okay.
Yeah.
The sadness and amusement. Right.
Okay. So if I'm talking about my cells, what am I looking at? How many cells do I have here? Four.
So, like, sadness expressed is one, sadness withhold is one.
Perfect. okay? Yeah, and this is going to be important so that when you look at this table, you want to know sort of what corresponds to what, right? So I've got my mean expression for sadness express, sadness withhold, and then amusement express, amusement withhold. Okay. What if I wanted to pull my main effects? Where do I find the main effects? My means for the main effect of film condition. Yeah.
Under total, the bottom of each condition.
Perfect, right? So collapsing across instruction condition. This is the overall. This is the mean for expression rating for everybody who watched the sadness film. This is the mean expression rating for everybody who watched the amusement film. And Chris, which one for my instruction condition? Where do I find those?
The bottom where it says total expressive hold.
Yeah. So everybody who was told to express, mean expression, everybody told to hold, mean expression. And then what is this 2.10? What does that correspond to?
The grand.
Perfect. This is my grand mean, right? This is the average expression rating of everybody in the design, okay? This, and then corresponding standard deviations, things like that. I mean, it's a descriptives table, but you want to make sure that you can go through and identify and say, okay, this is what this is, because these are going to be important as we go through later on when I test certain types of things, okay? So we've got our descriptive statistics. Also want to make sure your cell sizes match up to who you think you've got into what there. Our Levine's test, we already sort of foreshadowed this, saying that this was going to be potential violation of homogeneity of variance. If I go through and I look at my Levine's test here, I see I have a p-value of 0.029, suggesting that I may have violation of homogeneity of variance. What's the one thing with this design I might not get too worked up about this from context? Yeah.
The Likert scale, like rating.
Okay. So one thing about like the Likert scale, have you asked Kyle about Likert scales yet?
No, I'm sure he doesn't like them.
But he's sort of in terms of sort of technically what constitutes a Likert scale or a Likert type scale and things like that is, yeah, it's
I bet he has a really long answer.
yeah, it's interesting. Like but
he doesn't watch these videos, does he?
What's that? No, I don't think so.
I bet he does. What's Chris saying?
Right. What's Chris about? Okay. What is the thing that we might want to sort of take into account when we're interpreting the Nick?
The overall sample size?
Yeah. Why is that?
It's more robust to violations because with greater sample size, just more acute differences are going to be noticeable within this test.
Mm-hmm.
Be kind of more profound.
Well, kind of. When we're thinking about sort of this statistical picture, what I know, what's the number one thing that impacts my statistical test consistently? Sample size. What's my sample size looking like in this data set?
Almost 200.
Yeah, I got close to 200 people. So what does that tell me about the how sensitive is this Levine's test?
Very sensitive.
Very sensitive, right? And so I've got something that is 0.029, suggesting that, hey, at least based on these data are somewhat inconsistent with the hypotheses of equal variances across these. But I also know I have a lot of people in this sample, right? So I know that this test is going to be pretty sensitive to potential violations. So is my assumption that like, do I need to have my variances to be identical across these respective populations? Probably not, right? So I'm still probably going to use my corrected test just to be safe. But if you ask me if I was super concerned about violations of homogeneity, variance, and completely different things going on in different cells, probably not too worried about this. The other thing too is if you get into nuts and bolts of like Levine's test and homogeneity, variance, and stuff like that, you know that Levine's test is pretty sensitive to non-normal data. So these data aren't bad, but they're not perfect, right? So there's some things. So the thing that I want you guys to be aware of is even when we're just seeing things in possible violation of homogeneity and variance, I want to take this into account and saying, well, our sample's pretty large, and it's possible that this is picking up fairly minor deviations across variability in these cells. And so, yeah, we're going to want to probably take steps to use some corrected tests, but I'm probably not going to fly off the handle. And I wouldn't say that non-constant variance is a defining feature of these data. My test is pretty sensitive, and so just wanted to take that into account. Okay? Does this make some sense? This is, again, the same thing I see when I review papers. Someone sees, they give homogeneity of they go, the Wiggins test is like 0.04 or something like that, and then like lots and lots of discussion about sort of the violation of homogeneity. Like, maybe it doesn't look like it's too value. Just sort of not wanting to sort of run out out of the building, screaming the sky is falling, sort of based on stuff that's probably not super soon. Same kind of thing though in the set that you just put together, right? You found for that pilot study in problem 3, didn't have violation of homogeneity of variance there, right? Or things didn't come up as the Levine's test wasn't significant there, but there's also like 5 and 6 people in a cell, right? Is that test very powerful? No, like you would have to have some pretty massive discrepancies in order for that to pick anything up, right? So always wanting to take this, a statistical test is a statistical test. It all operates on the same principle, so wanting to use context and sort of making sure that you've got a good interpretation of things. All right, so let's get into the meat and potatoes of this stuff. Tomorrow, what are you seeing in terms of the between subjects effects in this table here?
It looks like we are seeing some main effects, but not an interaction.
Okay, so what do you got a main effect of?
Like film condition.
Okay, you got a main effect of film condition and a main effect of
Instruction.
Okay, and then where's the interaction effect?
Film by instruction.
Yeah, and so what do we have going on film by interaction? Film by condition interaction.
It doesn't reach like traditional significance.
Okay, we could say, might just say that so we don't have overly compelling evidence for a dependency between a film and instruction condition on expressive behavior, right? We could also say that these data are generally consistent with the null hypotheses of independent effects of film instruction, right? I mean, right? I don't know, but again, you know, traditionally what we might identify this as a marginal effect. How many people we got in the sample? Got a lot of people in the sample, right? So I don't know, right? If we're just looking at our main effect of film, right? And this is where these marginal means, when you're going through and plotting things out, use your observed means, not your marginal means, just because your observed means are what you're actually looking at. But of course, you use marginal means is a nice way. They'll be a little bit different than your observed means because these are like adjusted means. But if we go through and take a look, and so we see that we have a main effect of film. Chris C., can we interpret that main effect of film?
Well, it definitely depends, or it seems like we have a lot of evidence that it depends on the type of film, or the expression depends on the type of film.
Right. Expressive behavior depends on film. And so based on this output, can you tell me exactly what the main effect of film looks like?
It looks like the more, if you're in the amusement condition, you have a higher chance of, or you have higher expression relative to the sadness.
Perfect. And how did you decide that?
The amusement condition has a higher mean than the sadness condition when you're just looking at the film condition means, and then the confidence intervals are also, they don't intersect at all.
Yeah, you're exactly right. Yeah, there's confidence intervals are non-overlapping here, right? How many levels do we have in film condition? Two, right? And so if this in this omnibus effect, if I have an omnibus effect of film, do I have any, is there a need for follow-up tests or anything like that? No, it just says, yep, films are different. Well, there's only one way the films can be different, because there's only 2 of them. All I have to do is go down through and take a look. So I don't need to worry about any follow-up tests or anything like that with this, because it's clear how this goes. Now, if I had 3 films and there was a main effective film, could I determine sort of the specific nature of that effect based on my output? Probably not, right? I would need to go through and run some follow-up analysis. But for here, when we just have 2 levels to my factor, this is all I need, right? Also, what happens if I take so this F statistic and take the square root of that? What do I get? A t-test, right? Because this is a 1 degree of freedom test here, right? So F and T are going to be identical here.
I know, because I did all the Fs for the problem set.
Right? So going through and sort of knowing that relationship can be helpful for different types of things, right? Because what I could do then, if someone reported this and they just give the F for that, but they didn't give an effect size, and they just said, so this one's bigger than this one, I can take that F, take the square root of that, get a T, take that T, turn it into a D, and now I've got an effect size, right? So understanding sort of how to go back and forth between this stuff can be pretty helpful, okay? Alicia, same thing for instruction. Looks like we have a main effective instruction. Can I interpret that instruction effect based on the output here?
Yes.
Yeah. So give me an interpretation of my main effective instruction.
Express condition is, the express condition has higher mean score than the non-full condition.
Higher mean score on what?
On the ratings for the films.
Yeah, the expression rating. Right?
Expression.
So my people who I allow to just naturally watch this film in sort of behavioral coding are demonstrating higher levels of expressive behavior than the people who I told to withhold their emotion. Does that make sense? Yeah. Does this address sort of the questions that my reviewers had? Yeah. It looks like it looks as though my instruction manipulation was effective. Those individuals who I told to inhibit their expression did it to a greater extent than the individuals who were allowed to freely express emotion. Okay. So in this design, I would say, what's the magnitude of this film in this inhibition condition, or those tests? Are those big Fs? Those are really big Fs, right? If I wanted to go through, and again, this is where if I go pull up my base factor here, right? And I can go through and I can say, all right, I'm going to go through and take a look at, double click on this. Copy that and drop that into p-value on here, right? Gives me an S for my main effect of film. I've got an S value of 23. That's pretty compelling, right? My base factor is over 200,000, right? Basically, assuming that I've done a decent job of it so that I don't have weird methodological stuff going on, right? And what we're seeing is we have greater levels of expressive behavior in response to the amusement film relative to the sadness film. And again, if I take that p-value and just paste it here, it says 1.03 times 10 to the negative 7th, right? So I can go through and sort of make strong arguments, or make a strong case there. Same thing for instruction, right? We go through base factor here, 23, right? But then I might be interested in this interaction, right? Okay, you got an S value of 4, which is not different than my S value for P equals 0.05, right? My base factors suggest that the alternate hypotheses of dependency across film and instruction condition on expressive behavior is about twice as likely. The odds of my alternate hypothesis is about twice as likely as the odds of my null of independence across those two factors. It's not hugely compelling, right? But what I might be interested in doing, who knows, depending on, so if, so I don't have strong evidence for this interaction effect, right? Probably if I just wanted to interpret my main effects here, that would be, it would be hard to argue against that. But particularly given the size of my design, it would be hard to argue that I have truly underpowered stuff here. Now, to detect small effects, I'm still underpowered, but I wanted to go through and take a look at my interaction effect. Again, we have partial eta squareds here. My partial eta squared here is 0.02. So that's sort of hitting about the boundary of a small effect within these data. And so I might, this interaction isn't super important to me, but if it was, kind of depends on whether or not we want to move through there. Okay. But questions on how we go through and sort of interpret this factorial design. Okay. So let's go through and just real quickly. So I've got my partial eta squared for film condition is 0.142, right? And so I might say that within these data, film condition accounted for 14 or roughly 14% of the residual variability in expressive behavior, controlling for instruction and the film by instruction interaction. Or sort of the same thing, instruction condition accounted for about 14% in these data. Instruction condition accounted for approximately 14% of the residual variability in expressive behavior, controlling for film condition and interaction, right? And so this language is just used to communicate that I know that we're talking about a partial effect. We're not talking about total variability. We're talking about just partial portion of variability that's unique to, or that's sort of left over after we cut out sort of that other stuff. Other thing too, when we go through and anytime you get something that looks like it might be an interaction term, very, very, very first thing you need to do is plot it out. Like, don't try and make any sort of interpretations. Get a visual representation of what this interaction looks like, okay? Again, plot it out, just do it. It's gonna make your life a ton easier if you can go through and take a look. Now we had an effect here that doesn't provide strong evidence for dependency across my film and instruction condition, but it's not exactly parallel here in terms of the lines, right? So depending on what this is, you know, maybe I might, if the interaction was why I did the whole thing, I might then go through and start to go through and maybe take a look at that. Okay. Questions about sort of just basically working through the omnibus stuff here. All right, so let's jump back into lecture stuff. So we've gone through looking at factorial designs in SPSS. So we'll go through this, kind of what this looks like. So walk through this stuff. Did I do anything? Pretty much covers it. In Stata, Alicia, what you'll do is you'll use this command here, and that will just go through and label or give you a code for each one of your individual cells. So that's nice. It'll just kind of do it for you. It's just labeling your cells so you can kind of see which group is group. And then your Levine's test, you'll run your Levine's test as if this were a one-way ANOVA, and it's going to give you the same Levine's test as everybody else gets in SPSS. And then here's what your table looks like everybody else's. Okay. You can also run your effect sizes here. So after you go through and run your ANOVA model, E-stat E size will go through and give you eta squared, confidence intervals, omega squareds, and these are all going to be, notice these are all partial A is A squared, partial A squared, just pops it out for you. Okay. Now, the one thing that you will notice, right, is that when we went through, we had a violation of homogeneity variance, right? So our Levine's test is significant, right? Now, when we have a significant Levine's test with our one-way ANOVA, Sally, what do we do? We do the robust, right? We look at our Welch's test. Do we have a Welch's test for this factorial design? No, we didn't, right? And so this starts to become problematic because my factorial design is so the assumption is no violations of homogeneity variance. In my one-way, I have a robust test for that, but SPSS doesn't give me a robust option. It just says, yep, you violated, here's your test, there are your results that may be of questionable value, right? And this is kind of hard, right? Because rarely are the omnibus effects kind of at the end of the day what we want to, what we're most concerned about. And when we go and start looking at post hoc tests and sort of teasing things apart, we can do things that start to account for violations of the violations that we're seeing. But we're still concerned with these effects right here because we've got evidence of a potential violation, but none of these account for that, right? And SPSS is good at sort of going through and providing an option for that. And this bugged me, right? So we're like, yep, it's a violation, so if we're not going to do anything, why even test for it? Because if we're just going to pretend that so it's not there anyway, right? So one of the things within Stata that is nice is what we can do and what we've done here, because it's seen that I have a violation of homogeneity variance. I can run this analysis as a regression model with robust standard errors, and this is going to give me sort of a better test, given a better test of my omnibus effects, given my violation, given the violation of homogeneity as variance here. So here in this program, we're regressing expressive behavior onto film, instruction, and the interaction, and then saying, hey, we want to get a robust estimator of the standard errors to give us a better test of sort of these omnibus effects. And if you go down through and you take a look, so here's my main effective film, my main effective instruction, and then the interaction. With our uncorrected test, this is what we found. And we see that, at least in terms of, it doesn't look like there's too much of an impact for film. We start to get a little bit of a change for instruction, and then we get a little bit of a difference in terms of my interaction term here. So for this test, it looks like it doesn't matter a whole lot in terms of moving forward with stuff. But in later examples, like we have something that turns out in the uncorrected test, looks like, oh yeah, this is something that we have evidence for this effect, and we actually run appropriate corrections for it, it completely wipes it all out, right? So, I don't know, I haven't figured out a way in SPSS to go through and to, in an omnibus or in a factorial design to account for some of this stuff. No one outside of probably me worries about this stuff, but again, last time I checked, we're doing science, not free for all, whatever. So something to keep in mind in that violation, particularly if those violations are fairly severe, maybe be sort of wanting to question how much we can really infer from that omnibus ANOVA design given those violations, right? And you'll probably take care of it later on when you follow up with your follow-up tests, but so there are different ways to go through and address this. All right, so go through, we get our omnibus test, and we're feeling pretty good about that in terms of interpretation and things, right? But sometimes we're going to have interactions, and when we have interactions, we can't just eyeball our omnibus effects and sort of say, oh, this is kind of what's going on, right? We're going to need to do some additional things. But depending on the size of our design, our approach is going to start to look different, and it can start to get a little bit crazy, okay? So if I have an interaction, right? Remember that my interaction effect just says that the effect of A on, or factor A on my outcome is dependent on factor B. Or I can switch it around, the effect of B on outcome depends on factor A, right? And if this is what I find, I need to have some sort of approach to go through and follow up with this. I need to do something to go through and kind of tease this stuff apart, okay? So let's go back to our example from class, we're looking at a 2x3 factorial design where we've got difficulty has 2 factors, or 2 levels to factor A, with this difficulty 3 levels to factor B, which is arousal. Okay. How can we start to, what are our options for teasing apart this interaction? What comparisons can we make? So we're saying that the effect of arousal depends on task difficulty. How could we start to piece this apart?
We can look at like one difficulty level and see what the arousal is doing at the same time on the performance.
Yeah, I think that's a brilliant idea, right? What we can do is we can just go through and say, let's take a look at just 4 people who received an easy task and look at the impact of arousal on performance for people just doing easy tasks and just for people doing difficult tasks. Okay? What else could we do here? So that's one way. There's another way we could go through and take a look at this. What's our other option for comparisons?
Planned contrast.
What's that?
Like to do a planned contrast.
we could, but just conceptually, like looking at this, like what are our other comparisons we could do? So we could just look at differences in arousal level at easy and difficult tasks. What else could we do? What other options do we have?
Just flip it around.
Yeah. What do you mean flip it around? And what would that look like?
Instead of looking at arousal for like an easy task or whatever, you could do, you could pick the task and then look at arousal at the different spots. I might be saying the same thing.
Yeah, I think you're in the ballpark.
Okay.
So if we could look at impact of arousal, differences in arousal for easy tasks and then for hard tasks. What else could we do?
We look at easy. Okay, I'm not going to say this.
No, yeah, keep going.
We could look at easy tasks and hard, or we could look at task difficulty at different arousals.
Perfect.
That's
Right?
what it is.
We could look at differences between easy and difficult tasks at low, medium, and high levels of arousal. Right? So in this 2x3 design, there's a lot of different things that we could go through and look for, right? And so we can approach this with a series of planned contrasts, or we can go through and look at this with the post-hoc tests, okay? Now the problem is that before we decide on how to go through and do this, we need to have a good conception of how are we going to go through and take a look at this. What is the most important questions to ask, or things that we want to take a look within the context of this design, right? We could, for this, we could say, what's the effect of arousal on performance at different levels of task difficulty, right? And if we wanted to do that, okay, we're going to split up task difficulty. So we're going to take easy tasks, and we're going to look at the impact of arousal on task difficulty for easy tasks. What does that follow-up analysis look like? What is that? A one-way ANOVA, right? Basically, we've got 3 different levels, so what we're going to do is we can run a one-way ANOVA just for people completing an easy task, and then we can run a one-way ANOVA for people completing a difficult task, right? Or we can ask, what's the level of task difficulty, or what's the effect of task difficulty on performance at different levels of arousal, right? What are we doing there, Chrissy?
Oh gosh. So you're looking at the 3 levels of arousal and then looking at the task difficulty.
Right, and so what type of analysis are we talking about there?
Another one? No.
I mean, technically you could.
Yeah.
What would be sort of the more traditional way to go through to look at it?
You like a moderation almost?
Yeah. Well, the interaction is the moderation analysis, so we've already got that out of the way. If we're comparing 2 groups, what are we looking at?
Oh, just the t-test.
T-test, right?
Yeah.
T-test here, t-test here, t-test here, right? We can look at this either way. It depends on conceptually how we want to go through and do it, right? one of these might make more sense than the other. We have to want to go through and think about, based on our hypotheses and what we're expecting to happen, how are we going to go through and tackle this, what's important, okay? How many meaningful pairwise comparisons can we evaluate in this interaction? Let's ask this question first. How many possible pairwise comparisons are there? How many cells do we have? 6, right? So we've got 6 times 6 minus 1 over 2 is 15. We've got 15 possible pairwise comparisons, right? How many meaningful pairwise comparisons do we have? So, oh, I thought I was going to go through these. I thought I had animation here. Okay, so let's keep the t-tests. How many t-tests can we have here? So I'm going to stop picking on Chris. Someone else. Someone tell me you're just on a roll, buddy. How many, CJ? How many? If I'm looking at differences in task difficulty across arousal, how many t-tests do I have? 3, right? I've got a comparison here, I've got a comparison here, and I've got a comparison here, okay? So I've got easy versus hard. I've got 3, okay? What if we start looking at pairwise comparisons, if we're looking at the impact of arousal for people assigned to an easy task? How many pairwise comparisons do I have here? How many tomorrow?
3.
3, yeah. I can look at low versus medium, low versus high, medium versus high, right? So I say at easy, I got 3 comparisons. What about hard? 3, right? How many total is that? 9, okay? Where are my other 15 comparisons that it's like physics won't stop me from comparing? Where are these comparisons going on? Yeah, okay. So say that again. You're absolutely correct. So what's going on? So I can look at low difficult and medium easy. Okay. Those are 2 means that aren't captured in here. Does it make sense to look at that contrast? No. Why not?
It's how we're interested in, I guess, just the way the study's designed.
Right.
That's not what it's intended to do.
It's not what it's intended to do, and I don't even know how to interpret that, right? So if I'm saying that people with a difficult task at low levels of arousal perform worse than people with an easy task at medium levels of arousal. We're crossing factors. I don't know what that means. That's not a meaningful comparison within this set. Like I don't know if the difference between that is a product of task difficulty or arousal. It's not a meaningful comparison, right? So we've got 9 comparisons that make sense to look at. We've got 15 total. If I tell SPSS to give me a post hoc tests for this interaction, what's it going to do? I'm going to get taxed for 15, even though 6 of those aren't even reasonable to even talk about or interpret at all, right? Now all of a sudden that's a problem, right? I just got penalized for interpret those. I should probably get slapped in a review for sort of talking about things that don't make any sense, right? And so this is why it starts to become important to have a good game plan on how you're going to go about teasing this apart, what's important. And even within the context of these factorial designs, even if it's completely exploratory, right? And all I'm going to do is I'm just going to look at all meaningful pairwise comparisons within this design. I got to be careful because now all of a sudden SPSS isn't going to manage my type 1 error appropriately. I'm going to have to come up with a strategy to do that on my own. Okay. we'll kind of see what's going on. Do people see why we only have 9 meaningful comparisons within this design? Okay. So this is always a good exercise too in our interactions to go down through and say, what are the possible pairwise comparisons that I could make that would make sense in terms of trying to map out your plan? So when we're talking about interactions, we're generally talking about what we refer to as our simple main effects. Okay, so we're looking at simple main effects that refer to comparisons that are made across individual cells, right? So I've got a main effect, simple main effect of factor A at each level of factor B. Okay, so here they go, right? 1, 2, 3 here, right? What's the effective task difficulty? Low levels of arousal, medium level of arousal, high levels of arousal, right? So we've got 3 sort of functionally could be independent sample t-tests here, right? Then I've got a simple main effect of factor B at each level of factor A, right? What's the effective arousal on performance for easy tasks, right? What's the effective arousal on performance for difficult tasks? And so, again, within our analysis that we ran, we've got a main effective task, main effective arousal, but then we've got pretty strong evidence against the null hypotheses of dependency of task and arousal, right? We've got a nice omega squared based on sort of the calculations we did here. So in this case, should we be talking about, can we talk about these in main effects? No, these are conditional effects, because the impact of task depends on arousal, the impact of arousal depends on task. So what we probably need to do is jump straight to the interaction and start working through simple main effects within this design. You follow me up to this point? Okay, so the question is, how do we go through and start teasing out and sort of looking at some of these simple main effects? We use linear contrasts, okay? And our linear contrasts, this is just the same stuff that you guys have already done, no different here. The only thing that we would want to do in terms of our linear contrasts is wanting this mean squared error term to be taken from your simple effects ANOVA table. Okay? So for let's say I had an a priori hypothesis. So based on this inverted U-curve for difficult tasks, my assumption was that people would perform, for individuals completing difficult tasks, that people completing medium or at medium levels of arousal would outperform people at either low or high, right? What's that hypothesis correspond to? We're looking at one versus the combination of 2 others. So linear contrast, right? What I would want to do here is I would want to split this file up, okay, and run a one-way ANOVA, just looking at difficult tasks, and then I would run my contrast sort of using sort of the simple effects ANOVA just from within the difficult group. And then if I had a different contrast for my easy group, would sort of split file, run that ANOVA separately, and then run my contrasts from there. Now the actual calculation of your contrast, now we're just back to one-way ANOVA stuff. The guys, you spend tons of work on this last set. You're all experts on that now. That's no different than what we had done before. We're just splitting this up. Okay? And then in SPSS will give you your corrected tests for violations of homogeneity, very high violations of homogeneity variance. So we'll give you this here. Again, you won't have to do that by hand. Just let the computer do that. For this last test, for this last set, unless I tell you to do something by hand, use your statistical programs, right? You don't have to worry about cranking things out unless I explicitly say do this by hand. Okay? So in terms of our contrast, this is generally what we'll be doing, right? Because what ends up happening is we have, if this is the more conservative way to do things. Now, if I have a perfect design where I don't have any violations of homogeneity variance, everything's balanced, Tradition would say that I can capitalize and just use my mean squared error out of my overall factorial design. Right? The problem is, how is my mean squared error? Well, actually shouldn't be different. We're sort of separating that out. We'd run this from your simple effects ANOVA. This is just going to be kind of the best way to go through. It's going to be probably the most responsible way to go through and do this, as opposed to pulling mean squared error term out of your overall factorial ANOVA. Okay. So simple main effects for my effect sizes. Again, we're just going back to, if we split the file up and we're using our ANOVAs or our t-tests, now we're just back to old stuff that we've done before. Effect size for a simple main effect in our factorial ANOVA is still given as the value of our contrast over some error standard deviation. But once again, so the question here starts to become, how do I go through, and what do I use in terms of my standardizer, okay? Remember, so we've gone through and done our example, looking at task performance across temperature and humidity conditions, right? In our one-way ANOVA, so our mean squared error here, it looks at variability not systematically correlated, associated with temperature. So we've got total variability due to temperature, everything else is error. In our factorial design, we've got temperature, humidity, interaction, right? And so decided what happened to my error term in my factorial design.
It's all the factors that you didn't consider
Right.
in your variable.
Absolutely. And how does it compare to sort of my variable, my error variability in my one way?
It's everything that's not temperature.
Right. And so here, if I just look at temperature, but in this design, if I account for humidity, where did variability attributable to humidity go in this design? In my error. So if I systematically model it, what happened to my error term in my factorial design?
It's not, it would like go down.
It gets smaller, right? And so this is the concern with sort of using and pulling that in my overall factorial design, pulling my mean squared error term. The concern is it's great for power, okay? And it's nice, it makes for a more powerful design. But if I'm wanting to go through and calculate effect size, my concern is that I'm going to systematically inflate my estimate of effect, because sort of this error term is starting to get smaller and smaller and smaller, given the more stuff that goes on. Again, remember that we're always concerned with inflated effect sizes within our design or within our research. Just the fact that if I find something that's worth publishing, chances are I probably overestimate my effect size anyway, right? And so we want to do things that avoid systematically inflating that estimate of effect. And so the concern with just pulling that error term from the overall factorial ANOVA is that mean squared error is going to be an underestimate of variability, and so it's going to jack up our effect sizes. Okay, so a couple of different things in terms of options in calculating our effect size. Within Howell's book, he makes an argument or suggests the possibility of creating a standard deviation term based on your overall ANOVA table, sort of just looking at the sources of error within sort of whatever it is that you're looking at, right? So in this case, if I'm wanting to take a look at variability of sort of an effect size for temperature, okay? What Howell is saying is if I have temperature, so we got 3 levels. So let's say my hypothesis is that people in 70% conditions, in 70 degrees are going to outperform people at 50 to 90. Okay, so that's my linear contrast. I'm saying this group compared to these other 2 groups. What Hal would say is I would first calculate the value of my contrast there. So look at the difference between my 70 degrees versus the combination of 90 and what was it, 50? Yeah. And then what I would do to calculate my standardizer is I would go through, and from my overall factorial table, I would take my sum of squares error, right, because that's just what's left over. But then I'd add back in sum of squares humidity, because my contrast doesn't account for humidity, right? Add that back in, and also this doesn't involve the interaction. So add that sum of squares back in, and then take that divided by degrees of freedom for air, degrees of freedom for humidity, and degrees of freedom for the interaction. Okay? And so the idea is that what I'm doing is I want to get an appropriate standardizer. If I just pull the mean squared error out of this, I'm using a standardizer variability that's had stuff sectioned out due to factors that aren't involved in my contrast, right? My contrast here has nothing to do with humidity or the interaction. And so if I just pull my, take the square root of my mean squared error here, what ends up happening is I'm capitalizing on the fact that sort of that variability has been pulled out when that's actually relevant to calculating my effect size here. My effect size is just looking, all it's concerned about is the difference in performance of people performing in 70 degrees versus 90 and 50, right? This is going to be better. I mean, it's going to make my effect size look better, but it's probably not going to be representative of the true difference that we observe here. So Howell is saying what we can do is create a effect size specific error term based on adding this stuff back in. Okay. But this is pretty involved, right? Other options that we have, again, same effect size measure that we've used, or the effect size formula that we've used throughout this whole series of lectures, but just going through once again, just making a decision on where we're pulling our stuff from. From our, we could take the square root of the mean squared error for our factorial ANOVA, but the problem is that's going to systematically inflate our effect size, right? It's going to make it look too big, right? So another thing we can do is we can go through, and as we've done before, just take the square root of the mean squared error from our simple effects ANOVA, right? So when we go through and we say split the file and look at the impact of arousal on performance just for easy tasks and hard tasks, right? From that simple effects ANOVA, because we're going to get a one-way ANOVA for easy tasks, we're going to get a one-way ANOVA for hard tasks. What we could do, assuming that we have a balanced design, no violations of homogeneity and variance, we could just take the square root error from that mean squared error, from that simple effects ANOVA, and just use that. That might be a good option, okay? Or what we could do, if I have unequal cells and in addition to violations of homogeneity or variance, what I could do is just take the square root of pooled variances from whatever cells are involved in my in the comparison and the contrast that I'm making, right? We could also do that. Or standard deviation control group here. The idea is that when we're going through and we're calculating effect sizes for our simple effects, probably what we're going to want to be doing is relying on simple effects ANOVAs, or if we only have 2 levels, right? Just looking at using the sort of t-tests for the 2 groups that we're looking at, as opposed to pulling our term from our overall factorial table. You were kind of following along with the concerns about just grabbing this term and just using that. Okay, so for my contrasts, thinking about where do I go? How do I do this? And this is why I said on the front end, it's very good to, before you jump into stuff, plot out interaction terms and figure out how am I going to go through and adjust this, right? For my planned contrasts, if I've got a balanced design, no clear violations of the homogeneity of variance, I can make an argument for pulling an error term from my mean squared from my factorial ANOVA, but probably unbalanced design, possible violations of homogeneity of variance, probably what's going to be better is for simple effects, pulling the mean squared error from my, or sort of going through and running a simple effects ANOVA, and then sort of taking things from there. Once I've run it in simple effects ANOVA, now I just have a one-way ANOVA design, right? And then so you can go in through there to get my effect sizes. I can go through and I have no concerns with reporting an inflated effect size. Use my mean squared error for my factorial design. Again, you probably shouldn't do that. If I have no clear violations of homogeneity of variance, take the square root of my mean squared error for my simple effects ANOVA. If I have an unbalanced design, possible violations of homogeneity of variance, use a pooled variance of the cells that are involved in my specific contrast. Or so there's always, if I have a design where I have a clear baseline and it makes sense to refer everybody to that group, then sort of class of delta is going to be an okay thing to do there. Questions about this? So this kind of covers our contrasts. And again, how are you all feeling with contrasts after sort of problem set 5? Feeling as though you have a good handle on how to do those within the context of a one-way design? Okay. For our interaction terms, if we have the interaction, you need to go through and do that. All it's going to be is just going through and splitting the file, and now I'm just looking at levels of here, levels of here, levels of here. You're just falling back on stuff that you've already done before. You just want to have a clear plan on how you're going to go through and do that. Okay. But our other options are post hoc tests. Right? Maybe this is completely exploratory. I have an interaction effect, and I just want to look at all possible pairwise comparisons to try and tease this stuff out. Okay. Thing is, we need to be careful in terms of, as our design starts to get bigger, the number of all possible pairwise comparisons that we can make starts to get pretty intense. So 2x2 design, someone tell me how many meaningful pairwise comparisons do I have in this 2x2 design? Yeah, so I had 4. Tell me where those 4 are.
B1 with A1 and then B2 with B2.
Okay, so we go B1 with A1, so we can go here, and we can go here, and then we got these 2 and these 2, right? So we got 4 meaningful comparisons. All right, we've got 6 possible pairwise comparisons, but only 4 that are meaningful, right? What about a 2x3? We just talked about a 2x3, right? We end up with 9 meaningful comparisons here. We've got, within A1, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So we've got 9 comparisons here. What about a 3x3? We're up to 18 here, right? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. We've got 10, 11, 12, 13, 14, 15, 16, 17, 18. 3 by 4. Now we're up to 30, right? I got a 2 by 2 by 2. Got 12. Okay. Here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. Yeah, 11, 12. 2 by 2 by 3, 24, right? Who wants to, okay, so you guys have gone through and been providing, what, in this last problem set. With the factorial stuff, you had to give me interpretations on 3 pairwise effects at most. How much work was that? How do you like to do that? Like times 7, right? This is what happens, right? Anytime we go through and start looking at, I'm deciding to go through and look at all possible pairwise comparisons, it starts to get a huge, massive number of comparisons. The correction that I need to apply to that starts to get massive. And then probably the biggest thing in my book that I get concerned about, now all of a sudden I got a bunch of random ass effects that I have to account for. They're almost certainly going to pop up, right? Stuff is going to come up as, oh, what I found is B1 in C1 is different than A1, B1 in C2, right? Is that meaningful? Probably not, right? But if I go through and it's flagged and it's come up as important, I'm assuming as a reviewer, if you tested it, you thought it was important to take a look at, so now you need to tell me what's going on with that stuff. And if I'm not interested in it, that's a lot of BS for me to try and make up to account for random stuff that's popping up all over the place, right? So this is the problem, just particularly with factorial designs, is that I just start to decide to look at all possible comparisons between all possible things. It starts to get really, really unmanageable, right? In terms of discussion, in terms of the narrative, you want to be very careful to the greatest extent that you can, particularly if you have a larger design. Be very, very clear on why you're doing it, what effects are going to be most relevant to your hypothesis or theory and things along those lines, and test those. And if someone else wants you to test other stuff, say, cool, here's mean standard deviations, go nuts, knock yourself out. It's not important for what I'm looking at, and it really starts to confuse sort of my narrative, my interpretation. Now I've got too much to talk about. Okay. So, for post hoc testing, do not request post hoc testing through SPSS for simple main effects for an interaction. What SPSS is just going to correct for all possible pairwise comparisons. Doesn't matter if they're meaningful, if they're not. So if you go through and do it, SPSS is going to tax you for a bunch of stuff that doesn't make it. It's going to, you're going to get charged for those 6, even though you had never had any intent to interpret those or could interpret those. SPSS is just giving you all possible comparisons for all possible things. Do not request these through SPSS within the context of an interaction. Your correction for your family-wise error, way too big, right? And it's going to reduce the power of your tests. So you want to watch out. You're going to have to come up with a plan manually by hand to say, what is my corrected tests? And then if I am going to go through, of those tests that I'm going to go through and take a look at, how do I go through and run this stuff? So, one option, and this is online stuff, how we'll put together, talking about using a modified two-key evaluation to go through and run post hoc tests within within these factorial designs. Okay, so what I would do here is what I can do with a modified two-key. Let's say I've got, let's use our 2x3. Let's say this truly is exploratory, and I could make an argument for how all 9 of these comparisons might be reasonable. Okay. So what I need to do now is come up with some sort of strategy. How do I correct for those 9 using sort of this post hoc two-key? Okay. First thing I do, determine how many comparisons that could be made. So here it's 9. 2, need to identify a value of R that provides some reasonable level of protection against my type 1 error. Okay. So if I got 9 meaningful comparisons, my 2x3. I could, remember, because in two-key we're using our Q table, and R is indicating the number of means in my comparisons. Well, what I could do, I need to find an R that accounts for reasonably 9 comparisons. If I set R to 4, that's going to correct for 6 comparisons. Okay, that's probably a little light. If I set R equal to 5, that's going to correct for 10 comparisons. A little more stringent than what I want to do, but probably I'll take that as a penalty for not having sort of considered what is most important. Probably, so I'm going to say, okay, I'm going to go with R, R equal to 5 in terms of my T correction. That's going to be a conservative adjustment, but I'm willing to sort of accept that, right? Other thing you could do, you could adjust your alpha, and you could look at, I'm going to go through it, let's say I'm going to go and set R equal to 4, but I'm going to look at, use R equal to 4 with alpha equal to 0.01. I don't know why you would do that, you could, right? But this alpha is another thing that you can go through and adjust. But for this procedure, let's say I'm going to go to choose 5, right? R is equal to 5. This is going to test for control for 10 pairwise comparisons. I've only got 9, but I'll just take the extra penalty and call this close enough, right? Then what I could do is I could go through and I could take my set R equal to 5 and calculate my critical Q based on my chosen R and degrees of freedom for my contrast. So how many degrees of freedom I have. Probably pull this from my, probably what I would do if I were going to do this, I would look at my degrees of freedom for my smallest comparison, right? Because I'm looking at pairwise comparisons, right? So if I've got an unbalanced design, I've got sort of the lowest degree of freedom that I would have is, so I would say I've got 18 people in sort of one group and 20 people in the other group, and that's the of the possible comparisons I would make, that would be the lowest degrees of freedom, 18 to 20, 28, so I'd have 26 degrees of freedom. Probably just set R equal to 5, degrees of freedom equal to 26, and calculate my Q for that. Again, we're using it, this is going to be conservative, but if I'm just going to run through and look at all possible comparisons, that's what I might do there. Okay? And then once I've got my critical Q, remember that Q and T are directly related with one another. What I can do is I can go through and derive a critical T from my critical Q, and then use that for all of my pairwise comparisons. Then what I can do is I can just run through an independent sample t-test all 9 of those comparisons. And if my test statistic exceeds my critical that I got here, then cool. I'm going to label that as something that I can talk about, sort of something that's sort of meeting sort of evidence for this, sort of based on sort of this modified 2Q procedure, sort of going through and using this this approach. Okay, so this is why in the previous lecture I went through and made sure that we walked through the guts of what's actually going on with 2Q, because if you understand what's going on, you can start to use this as admittedly imprecise way to go through when I get into factorial designs to go through and try and account for stuff, right? Now here in this case, I'm using degrees of freedom based on my lowest degrees of freedom pairwise test. And I'm using an R that's a little bit higher than what I would expect that corrects for maybe an extra test than what I would need to do here. But at the end of the day, my penalty within this strategy is going to be less than what it probably would be if I just asked SPSS to 2Q correct for all possible comparisons within this interaction. Okay. Questions about this? Okay. So this is how we can bastardize 2Q to go through and make it 2Q do the things that I want it to do. Okay. Kind of. Right. Other thing we can do is we can take a different approach, Benjamini-Hochberg approach, and again, I picked this up from Howell, going through and taking a look at some of his stuff, and had never heard about this before, but it ends up being really, really slick and something I've recommended to other people who used it successfully. So the idea behind Benjamini-Hochberg is sort of our alpha correction, our 2Q, and things along those lines are interested in managing your family-wise error, sort of alpha inflation, sort of as we typically think about it. Benjamini-Hochberg, so this is going through trying to manage our false discovery rate, right? We're looking at our family-wise error. Sort of our concern is like, okay, what's the probability of committing one or more type 1 errors across this set of analyses, right? It assumes that sort of my entire set of tests is problematic, is faulty if I make even one type 1 error, right? So I've got, let's say, 6 pairwise comparisons to make. Our traditional approach says if I make even, among those 6 comparisons, if I make even one type 1 error, the whole thing is garbage. So I've got to go through and correct for all of these to make sure that I don't make even one type 1 error, right? Benjamini-Hochberg, so this is a different approach. It's asking what percentage of significant effects are going to be false positives, right? This is a little bit different approach, right? So I'm saying, I just want to make sure that sort of my ones that I'm not sort of making, so what's the likelihood of me making a false positive in sort of these effects that are statistically significant? And so we take a little bit different approach. So for Benjamini-Hochberg, what we do is we determine a p-value, a critical p for each successive contrast, and your p-critical is calculated as equal to I, which is the test index, which we'll talk about in a moment, over k, the number of tests, times your alpha level. Okay. And then what we do is you set up your set of tests. All right. I don't know why Joe Dirt, like at some point I thought Joe Dirt was funny to put up on here. And I was trying to remember what connection, and I couldn't remember. Right? Right? It's like, I don't remember why it is, but it's still funny, and so I left it up there, because now it's just weird. So, what we would do with Benjamini-Hochberg, let's say I've got a 2x3 ANOVA, okay? What I would do here, I would go through and run a t-test for all of my 9 pairwise comparisons, okay? And then what I would do is I would, based on the absolute value of the t-test, line these up from my smallest test value to my largest test value. Okay, so we're ignoring signs, that doesn't make a difference, right? And then what I do within a Benjamini-Hochberg, so I want to control the false discovery rate for this set of 9 tests. So what I would do is I would say, here's my contrasts, organized in terms of my smallest test to my largest test. Here are the p-values associated with those tests. And then what I would do is I would index these starting from my smallest, so I've got 9 tests all the way down to 1. 1 is my largest test. And then I'm going to calculate a p-critical for each one of these. Okay? So I is my index, k is the number of tests, alpha is 0.05. Right? So here for my first test, this is my smallest test statistic. The index for this is 9. I've got 9 comparisons. My p-critical is 0.05. Benchmark transfer. Right? And then I go down to my next one. Right? So the index is 8. 8 divided by 9 times alpha. My p-critical is 0.044. Right? So I've still not sort of made it here. It's okay. And so I go down through and continue down until I get down to here. Right? So for my, so what is this? Say this is my 6th test. Right? This is 0.033. I've exceeded this, right? And so it's going down. So what Benjamin Osprey is doing is it's controlling, sort of wanting to manage the number of significant effects that turn up as false positive. As I start to get farther, sort of stronger and stronger effects, my critical value or my critical P to match that, so it's getting more and more stringent, right? So this is a very different approach than saying all tests have to meet this certain criteria. I go through and I run sort of all these tests, having no sort of a priori hypotheses on what's going to be different. And as I proceed to get sort of more and more larger and larger tests, my critical value for that starts to get increasingly stringent, right? What's nice about this is this whole system is put together to control for any number of tests exploratory tests that I want to go through and put together. I can do and have done a modified 2-key, but it's not super precise, right? I'm kind of ballparking it, trying to get it so like, oh, this is, again, kind of a manageable something for this. This is much more flexible in terms of sort of laying out more precise control, again, for false discovery rate as opposed to sort of our traditional approach here. Okay. Cool. Understand, kind of see what's going on with this. So it's kind of like sort of a Demsitic or a von Fermi, except for I'm not calculating one critical P for everything. My critical P value gets increasingly stringent as sort of my tests get sort of larger and larger. So it's more adaptive. Questions? All right. I don't know, this is 3-way interaction, or 3-way designs, things along those lines start to get increasingly complicated. And look at that, we're done. I leave the fun of that. We still got an hour, right? Back in the class is down to 5. All right, so what we'll do next time, we're all the way through lecture material. What we'll spend our last class doing is working through a couple of different examples to just give you different looks on how we go through in the presence of interaction effects, how we start to tease things apart, sort of run through tests and things like that. We're not going to worry about anybody who need to walk through more screenings. Feel like we're pretty good on screenings, right? So we'll just jump in and work through examples and sort of put together a plan for, okay, if we have interaction, how do we go through and start to pull things apart and stuff. Does that sound good? Okay, cool.